Hello everyone, I'm Ke. Welcome to our presentation on our CVPR 2024 paper, SCE-MAE, Selective Correspondence Enhancement with Masked Autoencoder for Self-Supervised Landmark Estimation. This work is done during the internship and module phase. The Self-Supervised Facial Landmark Estimation aims to learn an image encoder with unannotated data. The learned image encoder should be able to encode face images into dense and distinctive feature representation, which can be used to boost the performance of downstream facial landmark estimation tasks, such as facial landmark detection. Existing self-supervised facial landmark estimation methods always follow a two-stage paradigm. In the first stage, they use some existing instance level as self-supervised methods to pre-train a backbone network, which only optimizes a single global feature for each image. Then in the second stage, they will extract hypercolumn from the stage 1 backbone by stacking the intermediate feature maps from different depths. Lastly, they optimize the correspondence between every local feature. Though these methods have been shown to be effective, there are three limitations. The first one is that only adopted instance-level SSL method, neglecting the fact that downstream facial landmark estimation tasks are dense prediction tasks, which require fine-grained local representations. Secondly, the hypercolumns are memory-intensive, which limits their application and scale. Lastly, full local correspondences are naively optimized for every local feature, which may distract the model by focusing on unimportant non-landmark regions. To overcome the three limitations above, we propose our framework, SCE-MAE. In the first stage, we adopt Masked Autoencoder, a region-level masked image modeling-based SSL method to pre-train our VIT-based backbone. Given an image, it will be firstly randomly mask out some portion of the image patches. The unmasked patches will then be encoded into patch-level features by the encoder, and the decoder will try to recover the original image from the encoded embeddings. Because of the dense reconstructive nature of the masked encoder, it is capable of capturing rich local details in the first stage, and thus is more suitable for downstream tasks. In the second stage, we first leverage the CS token learned in the first stage to compute the CLS similarity map between the CS token and all image patch tokens. Based on the similarity map, we distinguish the image patch tokens into attentive and inattentive tokens, where attentive tokens cover the landmark regions and inattentive tokens are unimportant non-landmark regions. The inattentive tokens will then be clustered by a simple density peak clustering algorithm to output cluster centers. After that, the inattentive tokens will be approximated by the corresponding cluster centers in our correspondence approximation and refinement block. The approximated feature will finally be optimized by our novel locality-constrained repellence loss, in short, the LCR loss. The LCR loss consists of three components: the correspondence, which measures the similarity between local representations; the locality, which measures the spatial distance between local features; and the repellence identifies the relationship between image patches and applies different weights to different relations. There are three possible relationships: attentive-attentive, attentive-inattentive, and inattentive-inattentive. The inattentive-inattentive relation is of the least importance and should not distract the model's focus. Now let's take a look at some of our experimental results which demonstrate the effectiveness and robustness of our SCE-MAE framework. Here we show some quantitative results of the comparison between our method and the previous state-of-the-art. The results are grouped by feature dimensions. We reduced error by 22 to 54% on landmark matching and 6 to 18% on landmark detection, which demonstrates the effectiveness of our method. The ablation study also proves the importance of every proposed component in our method. Here we show some qualitative results of our method and the previous state-of-the-art. We can see our method consistently outputs more accurate landmark predictions even when landmark is occluded by glasses. This demonstrates the robustness of our proposed method. Finally, we summarize our contributions into 3 points. First, we are the first to leverage Masked Autoencoder, a region-level masked image modeling-based SSL method that naturally better suits the landmark prediction task. Secondly, we use the vanilla final feature map to circumvent the operation on expensive hypercolumns. Lastly, we introduce the correspondence approximation and refinement block to identify and approximate the features of unimportant non-landmark regions, and operate a novel locality-constrained repellence loss to directly hone only the salient correspondences. Thank you.